Hello, everyone. We're back on the air. Sunday. Hopefully, a great day wherever you are. It was a pretty good day over here, Germany. We had a very sunny day.
Yeah, I like the room temperature outside.
Yeah, we did pretty good today. Anyways, I'm going to continue this week with an analysis of quantum mechanics because the subject is quite extensive, really, and we're not done yet with everything we got to say about quantum and how it relates to the rope model and so on. And what we got to do is find out what these people are investigating. I mean, you have many centers in the world, all these accelerators, and their counterparts who work at universities who do the theorizing of what these guys discover supposedly in the lab. What they, you have the accelerator people, the particle physicists, as they call themselves. I call them particle mathematicians because all their explanations require magic. And then you have the theorists who analyzes what these guys do and tries to figure out, what's really going on in the subatomic world, especially. Anyways, we started the week with the gluons. What is the problem we've got with it? We start with the gluons, and here you see the gluon, and the gluon is kind of weird because it's portrayed not as particles, but they're portrayed.
What is a gluon?
Oh,
we got an atom. Let's start at the atom.
Okay, we have the atom, and we can go with the simplest atom here with hydrogen.
I think we all know what an atom is.
Do we? Oh, please explain it to me. We don't know. I don't think we know.
Go even bigger. All things are made of atoms.
Well, yeah, all things are made of atoms, and we thought that was the indivisible. That's what atom means. The word comes from the Greeks. Days of Democritus, even before him, his boss Leucippus, and and they came up with this notion of the indivisible. What I like about what Democritus at least summarized was the fact that he said that all there is atoms and empty space, and I'm not sure if he meant that literally or exactly, because that didn't leave much room for the gods, unless the gods were made out of atoms, right? Maybe he pictured them as made out of atoms, then it's okay, but maybe he didn't have room for the gods, right?
Godly atoms.
Yeah, and so that's somewhat of an unknown what Democritus was really referring to. But let's assume we have atoms in empty space. That's pretty good. I like that in many ways. So we don't really know what he's referring to. But the question is whether, and I'm almost sure that he was referring to the fact that the atoms are like little balls out there, discrete balls, so there's a bunch of particles in the world. And, and under the rope model, all these particles are interconnected. And under quantum, they're not. So that's the major difference that we've got between quantum mechanics and the rope model of the atom and light. And the other thing that's missing, from Democritus' notion of the atom is that he didn't say that they were interconnected. In other words, if all these atoms are interconnected, what are they connected by? And in the rope model, you have the rope, electromagnetic rope connecting all these atoms. That's how light is sent from one atom to another through a torsion along the rope, and that same rope serves for the purposes of gravity. So that's totally different than what quantum has with all these isolated particles. They have no description, let alone an explanation for gravity. There's no description for gravity in quantum mechanics. But then you have the gluon, and the gluon is similar to gravity in the sense that it holds the quarks together, as you can see there in the picture.
What are quarks?
And the proton and the neutrons within the atom are made of quarks.
So we got
3 quarks
atom
each.
made of protons, with protons made of
Quarks.
quarks connected by gluons.
Connected and connected is that's the
That's
weird
what we're
word.
gonna get into.
Yeah, that's the weird word.
We just need a quick summary. What's a gluon?
Yeah, the gluons supposedly are part. In fact, here's the real way you should visualize gluons, and the gluon is supposed to. Oh, let me pull this down right. The gluon is supposed to be a little ball or that goes between quarks. In other words, the quarks are sending these balls at each other. They're throwing balls at each other. And the gluon is supposed to keep them together within the neutron or the proton. And you say, how is that possible? By throwing a stone, do you keep these three guys together? And the way they get around that again is, they put the spring in there. They say, well, this is the way they show it to the public. They say
the ball acts like a spring.
Yeah, and so we have a problem because this is misleading. This is very misleading because the gluon is supposed to be a particle, not a bed spring, which is the way I labeled these springs that. And by the way, this image comes from CERN. So this is their way of showing the world, oh look, this is how we keep the quarks together. We've got these springs in there. How do they explain it? They explain it in reverse. They say, look, if you try to pull a quark farther and farther apart, you need more and more energy. So they simulate it with a bed spring, like saying, it takes more and more energy the farther the quark is apart. Yeah, fine. How do you explain that with particles? You can't, so they put the bed spring. That's how the bed spring came into being, that notion. And they're not the only ones. You'll see always, wherever you look on the internet, you'll see the gluons always portrayed by a squiggly line. And that's this bed spring, which is supposed to represent more and more energy or force is needed to pull a quark farther apart from its proton or neutron. And that's one problem. We can't, quantum cannot explain pull, the force of pull, which is another type of gravity. Another gravity is a force of pull. The gluon is a force of pull. They cannot explain gravity at all. They cannot even describe it. And same thing for the gluon here. They put a bed spring just to simulate it. And then we have another problem, which is that the gluon, really the quark that it's pulling together, is creating matter out of the void. You can say that it's creating, that quark is being created out of many gluons. As they drift apart, a new quark is created.
That's what they say?
Yeah,
they say when two quarks go apart, the gluon between them
turns into a quarks. And so...
and two gluons.
And
two gluons, right?
No, the new balls are quarks.
Yeah. But the quark between the gluon between them.
Yeah. Turns
into a total of 4 quarks and 2 gluons.
Yeah, that's again. It's the stronger the more energy you need to pull a quark apart. The farther you pull it out, apparently a new quark comes into being.
And a new gluon.
Why a new gluon?
I mean, the GIF you're showing right there shows it. You have 2 quarks and 1 gluon, and then you end up with 4 quarks and 2 gluons.
Required to separate quarks produces quark-antiquark pairs. Okay, that's the antiquark pair, by the way. Long before they are...
You're reading. I'm not talking about the text. I'm talking about the just what we're looking at.
And what are we looking at? I'm looking at a quark and quark and antiquark. Okay.
Okay, a quark, antiquark, and a gluon, right?
Where's the gluon?
The stretchy thing in between.
Oh, okay. Because you're supposed to look at that stretchy thing as a gazillion gluons.
Oh, okay.
You're not supposed to see it as, oh, that's one gluon. No. What these guys have done is simply... It's so misleading that it's even very hard to explain what they're doing because the image doesn't reflect what they mean by the gluon in the standard model, which is that a gluon is supposed to be a discrete little particle that runs between quarks, or even between a quark and antiquark for that matter. But here they're creating a quark out of this elastic medium, which is supposed to be this bed spring, which they're stretching, and
which is actually a series of balls.
That's the point. The point
So
is that it's
series
not
of
one
balls
spring.
between
That
these
spring
balls.
is supposed to represent a series of balls, a whole bunch of
So
balls.
the more you pull these two quarks apart, the balls between them become more and more until they're so far apart from each other they don't bounce between quark and anti-quark.
Now
A
they
and
create.
B.
Now they create one.
They bounce between quark anti-quark A and quark anti-quark B,
Yeah.
but they're no longer in communication with each other. The gluons. It's like you split the
Well,
gluons in half.
I don't know about that because they're probably all over the place. You know, they're probably inside the proton and the neutron, like
Wherever
flying
you
all
need them.
around, wherever you need them. And the deal there is that, like, you know, Hans was saying last week, you know, it's like it's an infinite number of gluons. You don't have to justify the gluon. I mean, the quarks, no problem. Well, there's only 3 inside the proton. There's only 3 inside the neutron. Not to mention the anti-quark. We're not going to get into those, right? But just the quarks, just the straightforward quark, there's only 3. And there's always 3. 3 quarks for master mark. That's how they came up with this.
Proton per neutron.
Correct. Whereas gluons are unaccounted for.
It's just a stream.
Yeah, they're unaccounted for. And that's where the loophole is. That's where you create the loophole to your theory because you say, oh, we don't count gluons. There's gazillions of them.
But then these pictures of bed springs and these gifs of rubber bands are very misleading because it has nothing to do with what they're saying it is.
Right.
It should be a series of balls between them.
Yeah.
Getting and the quarks getting further and further apart, and the series of balls getting having to travel more between them since they're further apart.
Unless you just fill the space with more gluons.
But they're saying that the gluon. It's not that the gluons are passing on their gluonness between each other. They're actually going from quark to quark, right? So it doesn't matter how many there are.
I don't know.
This
is a good question. Yeah, but okay, fine. Yeah, that's how they show it. But I mean, it doesn't mean that, you know, remember, the 3 quarks are encapsulated always in a ball. See, they're always, the neutron and the proton are always portrayed as a ball. And somehow it contains 3 quarks. That means 3 balls make up 1 ball. And like I said, you put 3 balls together at home, do it in the presence of a trained quantum mechanic, and you won't be able to form a ball, a circular item with 3 balls. You can't. It always forms some kind of triangle, never a ball, never a sphere. But let's concede that. Okay, so you take 3 balls, you make 1 ball. The question is that other sphere, the one that encapsulates them, maybe that one's got gluons all over the place, even where the quarks are not throwing at each other. Maybe it just fills the extra space inside the neutron and proton. You know, all these little gluon balls there. All these marbles.
No, but you've shown gifs of that they put up where they showed the gluon bead going from quark to quark.
Yeah, here it is, and here it is. Here you see it going.
That's my point. That's their gif.
Yeah, this is their gif.
So
Again, this is theirs.
Gluon going from quark to quark.
Yeah, there you have it.
It's not that the gluon goes from quark to gluon, and that second gluon passes on the gluonness to the next quark. It's the gluon is traveling the whole path between each quark, so the further you take those quarks apart, the longer the distance that gluon has to travel.
That's the way I see it myself. But you know, we don't even know how these people picture it because
this is how it would have to be. The further those quarks go apart, the longer those have to go until it comes to a breaking point where the gluon
creates
gives up.
Creates a quark or anti-quark or whatever.
A quark or anti-quark, 2 come out of nowhere.
Yeah.
Which break the gluon chain, or not the chain, it's not a chain, it's more like an itinerary. It breaks the itinerary, the path it would have moved. Instead, the quark gives up, and the gluon gives up and just goes to this new quark, and then bounces from that new quark to the first quark.
It's like, you think of it in this way. You pull on the bubble gum, right? You pull, and at the end you create a ball
Yeah, but that's
at
wrong.
Some point.
That's my point. That's wrong. It's not bubble gum.
Okay, but that's the
It's-
way they
it's a
portray
series
it.
of
That's
beads.
one way that they portray
It's a
it. Right?
series of beads. If they're saying it's a particle, it's a series of beads no matter what they say.
Yeah. There's no doubt there.
I don't want to talk about bubble gum. We never talk about bed springs ever again. If they want to talk about particles, let's stick to particles. Let's stop with the metaphors.
Yeah, you cannot rationalize this from the standpoint of physics. Mathematics, it might make a lot of sense to them. Fine. They just put a number in the equation and they say, look, the more you stretch it, the more energy you need. They can talk in all those terms. They cannot make a picture or a movie out of what they're saying. They cannot turn that into physics. Again, mathematics is not the language of physics, because whatever they do over there and describe mathematically, they cannot put it on the screen for us to see. Whatever they put on the screen does not match, their equations.
Well, that's a different issue. See, that was a question I had for you last week that I didn't get to ask, which is, with the rope model, I'm sure there are equations that could describe the rope model accurately, where you don't have to come up with these kind of long-winded filibuster-esque equations that kind of try to plug every hole.
Yeah.
You'll probably if you stick to the rope model, if you give the rope model to a mathematician just to kind of mull over.
Yeah.
I'm guessing they could take, okay, what does the rope look like, and kind of they could extrapolate mathematical equations out of the rope model which fit more what they're trying to calculate in the first place. Like the equations will come out better if they even try to describe a rope than whatever they're trying to do now.
Yeah, and all this really is should give you a big headache, because you'll never understand it. There is no way you can visualize this. So you cannot visualize it under any possible circumstance. Okay, and so it's all very artificial in the sense that, first, it's unintelligible. They cannot make a real movie of what they're talking about. And their excuse for that is, well, mathematics cannot be put into ordinary language. No, that's nonsense. You should at least be able to explain what your theory is, what your explanation for the mechanism is. They can't do that with quantum, and they just say, well, we don't understand how Mother Nature does her stuff, and, that's not acceptable. Not after 100 years. You can't just keep saying, oh, we don't understand how Mother Nature does it, or the universe doesn't have to follow our way of rationalizing, all these fine prints that they put out there. No way. Physics is done with objects. You should have a mechanism for how the microscopic, the subatomic world works. They do not have a picture of it. They cannot give you a theory of the mechanism. No way. All they can do is tell you, look, this is what we do in math, and then this is the best way we can present it, and they cheat. Because
why are we talking about gluons?
Yeah, okay. I'm getting there. This is just the introduction again, covering a little bit of the subject matter last week. Well, we get to the standard model because today I want to get to the orbitals, which there's a couple stepping stones to get to the orbital, so please bear with me. First, we have the standard model, which we also covered last week. There's 17 particles in there, 6 of which are the quarks, and you'll see the G for the gluon there in the upper right-hand corner. Okay. And so this is the standard model, 17 particles. That's the basis. Again, we have so many other particles. Which isn't
a model, by the way.
Yeah,
it's a chart.
Yeah, first it's a chart, but
it's
then
not a model.
but then keep in mind that these are just the foundations. But then you have all these other particles. There's over 200 particles, they say out there. People who counted them. Over 200 particles, and we went over the quasars last week, and over the ones that form the exotic atoms. We no longer have electrons going around atoms. Now we have muons and anti-muons and all these muoniums.
But yeah, this standard model, which isn't a model, is a chart.
Yeah.
This chart is useless. This chart literally is meaningless.
And the gluon, as you can see, it's a letter G. There's no bed spring there. Unfortunately, they didn't put because if they put a bed spring, people might question, is that what a gluon looks like? And they just put a little dot there, and whatever that means. We have no pictures of any of these particles.
You just need a location for the gluon effectiveness to
exactly. And then you got to think about something here. you might say, well, they've never seen a gluon. Why would they put a picture? Well, it doesn't matter if they saw one. We don't care if they saw one. We have to see. One of my arguments is that if you're going to produce pull, like with a gluon, and the gluon looks like a hook, you can conceivably have. Let's see, where am I here? You can conceivably have two hooks together, right? You can have a particle that has hook shape. You can say, okay, I can understand how a gluon pulls on another one because they're hook shaped. Then you can, elongated hook shape.
You're moving the table a lot.
Oh, okay. So if you're pulling, in this direction, like hook against hook, we all understand why the gluon has this pull capability. But if there are two discrete balls, then you cannot explain how one pulls on another one. So it is important to know what a gluon looks like if we're going to explain attraction. Maybe there is a way of explaining it with a discrete particle, but the architecture of that particle is going to be very important. And I'm not talking about what the gluon looks like in real life. I want them to show me with a picture how the gluon is related to pull. Okay? And if it's a bubble gum, if it's a bed spring, no problem. Then they can say, look, it looks like a bed spring. I say, okay, now I can understand how it pulls on another quark because the two quarks are tied by a bed spring. But if the gluon looks like a little ball, there is no way they can rationalize pull.
Yeah, we have a problem. If they're balls, now we have a problem.
Yeah. And so that's the first issue. Then what is
the standard model?
What is the standard model? Well, the standard model
which
is
we went over last week.
Yeah, but I'm kind of going quick here now. The standard model particle physics,
just in case they want to recap, they can watch last week's videos.
Is the theory describing three of the four fundamental forces. Why? Because they cannot explain gravity. So there's three out of four. One is the photon, the electromagnetic, right? Then there's the weak, and then there's the strong, which is the gluon. Okay, so that's what it describes. And remember, it says describes. It doesn't say explain. They cannot explain any of this. So they say, look, we can describe them. Under no circumstances are they explaining. So fundamental forces, what are those? Okay, so let's go with that. The fundamental forces, also known as fundamental interactions, also known as fundamental forces, are the interactions that do not appear to be reducible to more basic interactions. And there's four fundamental interactions. The gravitational and electromagnetic interactions, which cover the entire universe. And then you have the microscopic world, subatomic world, which involves the strong and weak interactions. The strong being the gluon, okay? So that's the mediator of the strong force, of the strong interaction. Okay, so what is an interaction? Okay, Let's go step by step here. Each of the known fundamental interactions can be described, again, description, okay, mathematically, as a field. So now we say, what is an interaction? It's a field. Okay, so what is a field? We go step by step here. Is a field the same thing as, the foundation of quantum mechanics, which is the wave function, which is Schrodinger's equation, which is what he won the Nobel Prize for. In other words, the wave function is an equation that describes the interaction. And essentially it tells you where the electron is within the atom, okay? And it involves the word field, it involves the word interaction, it involves the word particle. All these are kind of meshed together. They just jump from one to the other. What is an interaction? It's a field. What is a field? Well, it's a particle. What is a particle? It's a wave function. So you keep going around these words, these terms, and you say, when are we going to get to the meat of the thing? Well, when are we going to get to an object that I can say, oh, I see what we're talking about. We're talking about a little particle here, or a little corpuscle, or a bowling ball, or a rock. No, you never get there. It's all mathematics, it's all descriptions, all quantitative descriptions that they do, and they give them these names. And they're very misleading because, they'll talk about particle when they don't mean particle, they talk about spin when they don't mean spin, and so on down the line. So they've invented all this language. And the first thing we have to distinguish between a field and a wave function, okay? The wave function, again, is the way that you describe a particle in a sense, because the wave function is an equation that tells you how spread out the field of a particle is, if you can think about it like that. There's this gradient going out from a particle, such as the atom, and it extends all the way to the electron. And the electron is also a little field that's moving around. There's no physical object there. It's a little ball with a field around it. What's the field? It's just a description of how the charge, and it could be also the what is it? The all these bees running around the electron that extend, in fact, forever. The electric field of the electron. So they use the word field for everything, and whenever you get down, they'll say it's a field. And so here they'll tell you that a field is different than the wave function. Wave function is a probability amplitude. That's what it is. In other words, it's the distribution of probabilities of something, right? Whatever it is, because we never know what it is, just values. And quantum fields are local, whereas the quantum fields operate over short distances, whereas the space-time ones act over long distances. So one is like a small field, and the other guy is like a big field. And even that's misleading, because they'll tell you that the muon field or a pion field extends to infinity. And all these fields superimpose upon each other, and they have no problem with that. They'll say, yeah, the muon field extends forever. The pion field extends forever. The electron field extends forever. So what are they talking about? Here you have like this charge. The electron has charge. It's got all these bees buzzing around it. And the bees get smaller or weaker as you go farther out, and you can take it all the way to the edge of space-time. And that electron, the field of that electron extends all the way up there. And the field of the next electron does the same thing. And of the muon and of the pion, all these particles have all these fields, which are, they say it's local, but it's not local, because when you come down to it, they say, oh, the field extends forever. Like the electric field of say, a charge like an electron extends forever. So we don't know what they're talking about when they're saying, the field is localized, like they say here. That's essentially not true, and it's also misleading. So we have more misleading behind more misleading. It's all just misleading, misconceived, misrepresented, mispictured, misimaged. So here we go with a wave function definition. Wave function is in quantum physics is a mathematical description of the quantum state of an isolated quantum system. So you have a little isolated particle, that's supposedly what they're talking about, and it just tells you something about the state, okay? Its state could be the charge it has, the location, how much energy. Those things involve the so-called state of a quantum system. Quantum state provides a probability distribution for the value of each observable. Look at all the strange language that they're talking about observables, and they're talking about probability distributions. What does this have to do with physics? I mean, we're not talking about the rock and how a rock hits something, or
talking about the chances of where the
rock is,
and talking about
and how much energy you need to move the rock.
What are the chances that the rock will be here?
Yeah, in fact, it goes here. Here you see the wave function equation, and this kind of synthesizes what they're talking about. Okay, and this is the famous Schrodinger equation. This is what he got his Nobel Prize for coming up with this thing. And what you see is the Planck's constant up there. Okay, mathematical nonsense that we don't need for anything.
This straight up looks like hieroglyphics.
Yeah, but that's why, we've got all these descriptions there. Quantity that describes that delta there, quantity that describes how the wave function changes from one place to another. So you have the wave function, and it changes at a different location, and that's what the delta upside down squared is. You have an imaginary number, which is the square root of -1. We have the mass of the particle being described, 2m in that case, right? You have the description of the forces acting on the particle, and then the final, that whole thing within the square, rectangle there, describes how the wave function changes its shape with time. What is all this about? Well, if you plug in numbers for this equation, right? If you keep plugging numbers, for each value you get a location of, for example, the electron around the atom, where it's at. What they want to know is where the little bead is at. That's what the Schrodinger equation does essentially. It tells you, look, with this we can map the entire itinerary of an electron around its proton or around its nucleus. Okay. So if you map this, if you go in there, you are able to map a region around the proton where the electron can be found. That's what it is. Now this region where it can be found is a verb. It's a location. It's a concept. Suddenly this materializes and turns into an orbital. What the Schrodinger equation does is map the orbital around which, in that region in which you can find an electron bead. That's why this equation became so popular. Here's a second definition. We need these so that you get a better picture. I'm going to have two more definitions of the wave function here. Here's another one. It says wave function are solutions of Schrodinger equation. Okay, and there you have the little equation again. A wave function in quantum mechanics is a description of the quantum state of a system. Again, description, quantum state. The wave function is a complex valued probability amplitude. Okay, so it's got to do with something with statistics, with probabilities. Okay, for the possible results of measurements made on a system can be derived from it. The state of such a particle is completely described by its wave function. Again, they're referring to the orbital. They're going to be talking about the orbital here, okay? And here's the third definition, in case you want to have a different viewpoint here. A wave function is any periodic function which tells us about the position of the particle of the medium in which the wave is traveling as, and there's the equation. The above equation represents a wave. Okay, so what are they doing? They're describing a region around in which you can find the electron, and then again, it's a probability distribution. Here's a picture so that you can see now. Where is it? Yeah, here. Here's a picture of the hydrogen wave function. Okay, those are the different shapes that the wave function takes when you plug in numbers into that equation. What is it? Okay, we're talking about wave functions of the electron in a hydrogen atom at different energy levels. Quantum mechanics cannot predict the exact location of a particle in space, only the probability of finding it at different locations. The brighter areas represent a higher probability of finding the electron. That's all it is. The darker areas, less probability. Okay? So the farther you are from the nucleus, the less chance of finding the electron there. The closer you are to the nucleus, the less chance you have of finding it there. So the electron is found anywhere in between the farther reaches and the closer reaches, the farther fence and the closer fence. Okay? Each orbital in an atom is characterized by a unique set of values of the three quantum numbers, N, L, and M. Okay? And these are important because they represent or respectively correspond to the electron's energy, angular momentum, and an angular momentum vector component called the magnetic quantum number. Okay? What are these people talking about? They're saying you need these three numbers. You can see the three numbers there under each one of those pictures. You'll see these three numbers, and that's what those three numbers represent. Essentially,
those are the three numbers you plug into the equation to end up with that shape.
Correct. And essentially what they're talking about, so that you don't lose track and don't get to too screwed up with this. They're talking about longitude, latitude, and the radius of the region around a nucleus, okay? So if you take from the center of the atom, you take its radius outwards, okay? And now you take latitude and longitude, that's where the electron can be found. That's one place where the electron can be found. Where's another one? Well, you plug in new numbers, new L, N, and M's in there, new values, and now you can find the electron over here. And they do a probability distribution, okay, and they map this thing out, and they end up with a region where you can find the electron. Does that make sense? Okay? In other words, mathematically speaking, what they're saying is we have three numbers: radius, longitude, latitude. Imagine I want to find you somewhere on Earth, okay? Earth is a round ball, pretty much, a sphere, we can say. And so what happens? I want to find you. How do I do that? And I can find you not only on the surface of the Earth, I can find you anywhere from the surface all the way to the center.
But then we have a problem.
Okay.
Because then you'd need three coordinates. You need longitude, latitude, and
radius. The height from the center.
Yeah, but that's of the entire atom, not from the atom to you.
From the center, the nucleus to you.
Yeah, but but it's not the radius of the nucleus to you. It's the radius from the nucleus to the edge of the atom.
Yeah.
But then might not be where you're at, how deep you are.
No. Let's get it right. What the equation does, if you plug in these NL and M, L, N, M, and M, what it does is give you first how far you are from the center of the atom. You could be farther out or closer in. That's the radius part, right? That number varies. You can plug in numbers for that. And if you plug in a little number, you'll find less and less probability of finding the electron because you're getting close to the positive proton. If you get too close, the proton will suck you in like a magnet. So
the radius, to clarify,
is changing.
Is it's not the radius of the atom.
No. It's the distance
between
correct.
The electron and the center. Yeah.
But think of it as a radius in the sense that at that point you got a sphere.
Yeah.
And that's where you'll find. It's like if the electron or the point that you're trying to locate is right at the surface of that sphere, and that's where the radius comes into play. Okay. And then you have longitude and latitude. So if I want to find you somewhere on Earth, I would need three coordinates, right? I would need first the radius, and let's assume you're on the surface, okay? So I want to find you somewhere on the surface of Earth. What would I use? I would use three coordinates. I would use the radius from the center of the Earth to the surface. And then I would use longitude and latitude and say, okay, you're in Paris, France. Okay, so as long as I have those three numbers, I can locate you. That's exactly what Schrodinger's equation does. Essentially, it says, look, the probability of finding the electron here at this point is such that if I plug these three numbers into the equation, it'll give me, and I do this over and over again with different numbers, I can map a region around the atom in which I can find you. And they call that region an orbital.
Around the atom or the nucleus?
Around the nucleus, I'm sorry. Yeah. So the issue is, this is a region. Okay? The wave function, this equation, allows you to establish a probability distribution where the electron bead can be found, and that region now becomes an orbital. That's why they call it orbital, because that's where the electron orbits. It's allowed to orbit in this orbital region. Okay, that's how the wave function field becomes a region, which is the orbital. Okay, now we have a tunnel or a sphere. It's a balloon. That's what they're describing. They're saying, look, with this equation, we can tell you what the balloon looks like. Is it flattened out? Is it elongated? Is it a complete ball? The wave function allows you to map a balloon. And I say, well, this is very simple. Why don't we just use the balloon? Because that's what they do. This is how they portray it. Here it is. Here's the wave function and how it converts into these balloons, which they call orbitals. All these are the regions where you can find, an electron bead. And as you can see, they use the three coordinates, x, y, and z. And you have the first one, which is the s orbital. These elongated ones, these are the p orbitals, S, D, and so on down the line. They have all these letters of the alphabet, right? And they just keep adding more and more orbitals. And all these are the ones where you can find an electron bead rolling around. In other words, the bead can be found anywhere in there, with higher probabilities in the shinier areas, less probability in the darker areas. Okay, that's what they're doing. So what they've done with a wave function is describe the shape of the balloons, right, for each one of these atoms. But you're not supposed to take these regions to be physical.
They're not actual balloons.
No, they're not actual balloons. They're just regions where you can find the electron bead. Now, keep that in mind, and it's important to keep that in mind because what they're going to do next is a little scary. They throw the electron bead away. They don't need it anymore. Now they're going to be merging orbitals, the regions. They're going to be orbiting, they're going to be uniting with one atom to another. They're going to be merging the regions. And now the regions are going to take on a real physical effect. And here you'll see it. Here's the first one, okay?
Wait,
here,
so you have two areas that overlap like a Venn diagram.
Yeah.
And then the areas connect?
The regions, let's call them volumes because they're not 2D, they're 3D, okay? So they're regions, and you think of a region not as an area like the surface of your plot of land. You're talking about a 3D region.
Like here. A room.
Yeah, and again, we're talking about balloons because suddenly they've converted these orbitals, which were just the region where we can find the electron bead. Now the region starts taking, we forget about the bead now, throw it away, we don't need it anymore. Now we have the balloon, and now let's talk about balloons and how the balloons merge. But what are we talking about? We're talking about the regions in which we can find an electron bead. And and now the regions touch and they hold the atoms together. The regions hold the atoms together. And they say, well, these are the regions where you can find the electron bead. Fine, if the electron, obviously they could not show how a little electron bead pulls on another atom. How two electron beads, one rolling in this orbital and the other one in this orbital, how they manage to get the two atoms together. So they forget about that and they start working now, again, very misleadingly, with the regions. They say, look, this region pulls on another region. That's what holds two atoms together.
Is that what they talk about when they talk about like sodium chloride connecting?
Exactly. Here I'm going to show you.
They talk about the orbitals connecting the sodium and the chloride.
Here, let me show you the picture because a picture is worth 1,000 words.
What chemicals did you use?
Here's two carbon atoms.
Oh, okay.
You'll see it right here in a second.
Okay.
We have two carbon atoms here. Okay? What do you see? You see balloons. Those are the wave function, calculations. And they calculate all these balloons. These are the p orbitals, by the way. And you can see that the p orbitals merge and form a molecule. Two carbon atoms. We're going to form C2, right? So they merge. Okay, so you have two atoms which are merging, but what's merging? What's bringing them or holding them together? The regions. And those are supposedly the regions where you can find the electron bead. So they're not showing you how electron bead pulls or holds two atoms together, how electron bead pulls on another bead and holds the two atoms together. No, they forget about the bead. Now they're going to do physics, or chemistry in this case, right? They're going to do chemistry and physics with the orbitals, with the regions in which you can find the electron bead. Now, does that make any sense?
It goes back to what we said the other week, where they're not interested in the physical interpretation. They only care about the areas of effect.
Yeah.
If this area of effect changes that area of effect, we don't care what's going on. Let's just talk about the areas.
And here you see another picture of that whole thing. Okay, look at this one. This one goes along the same lines. What you see here is, again, you see carbon and two hydrogens, okay, H2s, molecules, okay, and we're going to form methane, okay, and you can see that what merges are the regions. The s orbitals of the hydrogen merge with the p orbitals of the carbon, Okay, and they form this. This is the chemistry part. This is how they explain it in chemistry. They say, look, this is what's happening according to the quantum guy. You can see the p orbitals there, right? And they're holding the s orbitals of the hydrogen, which is just a ball, right? And what's merging are the regions. And they forget about the electron bead that's orbiting in the region. They just don't use that anymore. They're just describing the balloon. They're saying, look, that's an orbital where you can find it, the probability of finding an electron in this region. And now we're going to merge the regions. And we're going to hold these atoms together into a molecule with the regions alone. And what's in the region? The region is just the region where you can find the electron bead swirling around.
And I like how what's that gray stuff? The center ball. Why do they even
Which one? Coming up now?
I don't know where you're at. We always at different times.
Yeah, okay. This one, the big one, the big one.
But then they cover
That's
the center of it
because
with nothing.
No, because the s orbital is a ball, always a ball. The s
Well,
orbital.
The S orbital. Those are the hydrogen ones.
Not the center one, not only the ones on the edges.
I'm talking about the center one.
Right. The ones on the outside are the hydrogen, but remember carbon has the s orbital too. So they just show here how the p orbitals merge with the hydrogen, but then they say, okay, by the way, there is also an s orbital that encompasses the p orbitals. Okay? So that's what the molecule looks like. It looks like a big ball with little balls, and then they show you the inside of it there. Okay. See, they show you the inside saying, look, the inside of the ball has the p orbitals going all the way to the center. But what's one problem here? Look at the center. The center is the region in which you can find an electron bead. The electron bead goes all the way to the center or very close to the center. How can that possibly be if the electron is negative, whatever that means, and the proton is positive, whatever that means, and positive attracts negative? Yeah. Why doesn't the electron bead fall into the center of the nucleus of the atom? Well, yeah, but I mean, it does get close enough, and in fact, it goes to the other side, they say. It just kind of tunnels through the center, goes to the other side magically.
I thought it was teleporting.
Yeah, that's what it does.
But that's not tunneling, that's just appearing.
Yeah, they call that tunneling.
Those are two different things. Teleporting and tunneling, I think of them as two different things. Tunneling is traveling, and teleporting is just appearing.
Oh, I see what you. Yeah, tunneling is the scientific term.
Yeah, they try to get it. I don't know why even bother. With
you could say tunneling. No, but tunneling is also appearing. Tunneling is not going through. They just say it appears on the other side, and we call that tunneling because it's like it went through, but it just appeared on the other side. They don't explain how it went through. There's no traveling.
Okay, but the difference between tunneling and teleporting, you'd think that there's a time lag between tunneling.
There is none. They just say it suddenly appears on the other side. So tunneling is teleporting.
That's another misuse of language.
It is. Tunneling is a scientific term for teleport. Teleporting is Star Trek stuff.
Oh, you're not Star Trek.
That's Hollywood stuff. You're not going to use that in science.
I'm saying, right? I've never seen a car go into a tunnel and appear on the other side.
But that's what they do.
Skip the distance between them.
But you know how they do that? That's another important thing. The way they do it is they turn the particle, the bead, the electron bead, they turn it into a wave. Oh, okay. And the wave extends all the way to the other side instantaneously because the wave is everywhere at the same time.
So it outruns the pull of the proton. Is that what you're saying?
Yeah, it kind of skips over. It skips over.
It goes so fast through there that the proton doesn't have time to catch it.
No, in fact, it doesn't go through because I think it's misleading to think that it goes through. No, what they're saying is something a little different, I think, or how they visualize. They say, look, here's the electron bead. It's coming, gets close to the proton, and the proton's going to suck it in because the proton is positive and it's going to stick to it. Electron negative, proton is positive. It's going to stick to it. Instead of sticking to it, it turns into a wave and it appears on the other side and says, ha, I fooled you, proton. I'm on the other side now. And so it just kind of jumps instantaneously. So it appears, it tunnels through, and so now the bead, it turns back into a bead. Now it magically goes on the other side. So
there's nothing to be said about that. It's just
and that's so.
No further questions, Your Honor.
I rest my case. Okay, now let's go into science. Just what do we have? 10 minutes left. Let's do science now.
What? We're gonna do science?
Yeah, now we're going to do science with all this nonsense that we just went through. And here it is. Look, what they're talking about is a ball. They're talking about a balloon. What the Schrodinger equation does is describe a balloon. The balloon is the atom. An atom is a balloon. Balloon is an atom. Atom is a balloon. And what the Schrodinger equation does, it gives you the radius, the latitude, and the longitude of the region covered by the balloon. In other words, the whole balloon that encompasses or encapsulates the center of the atom, which is just a bunch of rays. You got to think of those as rays. The proton is essentially a little star with all the rays pointing in every direction. Think about what is it? A porcupine that's a rolled up porcupine, all the quills pointing in every direction. Think about a star, all the rays pointing in every direction, and it's encapsulated by this electron shell. The electron shell, I just show here the hydrogen atom, is that center. That's the proton dandelion, as I call it, all the quills pointing outwards. And there's the Schrodinger equation. It shows one point on the surface of that electron shell. Okay? What are we talking about? We're talking about radius, latitude, and longitude. That's how you locate that point on the electron shell. So whenever they say, look, we find the electron here, and then simultaneously at the same time we find it over there. Right, because they're looking at a shell. They're describing a balloon. That's what they're doing.
It is all over.
It is all over at the
literally
same time, and not because it's a wave or because it's a particle that's running around, but because they're describing a balloon. They're describing the rubber of a balloon.
Yeah, it's like they're trying to look at a balloon. They can only look at one spot of the balloon at a time,
and that's what the equation does.
And they're looking for the rubber on the balloon. They're like, oh, we found it here.
Yeah,
oh,
and we found it there.
But the whole thing is rubber.
Yeah, it's like oh, suddenly the electron's over there, and suddenly it's over there. Of course, it's all over because the electron shell encapsulates the proton star. And yeah, if you go to the center of the atom, you will find a star. What it is you've got this all the rays.
I wouldn't use the word star.
Well, I call it a proton dandelion because the dandelion points out.
The star makes it sound like they're made of stars.
No, I'm thinking of a little like like a little dandelion. Just think of quills pointing outwards from a center, okay, or all the quills converging upon a center. Any way you want to look at it, but that's what it is. The center,
like a porcupine.
Yeah, it's a rolled up porcupine, and all the quills pointing outwards, and that's what the proton is, and that's the reason the electron shell doesn't fall into the center of the atom, because it's a shell that encapsulates this star, this dandelion, this rolled up porcupine, any way you want to think about it. And all those quills that you see outwards are the ropes connecting to every atom in the universe. And what does the Schrodinger equation do? It gives you the radius, the latitude, and the longitude of where to find the electron, a point on the electron shell.
Why don't they find the electron in all the spots along this?
They do.
Area?
They do. They say the electron is spread out as a cloud. That's your cloud. That's the balloon. That's the cloud that encapsulates the atom. And that's what they show when they show orbitals like, methane here. What do you see there? You see balloons. But they say, well, they're not balloons. They're just orbitals. And what's an orbital? An orbital is the region where you can find an electron bead. And so they go through this whole, and what's the electron bead? Well, it's a field. And what's a field? Well, if you take the Schrodinger equation, you calculate and you get the field, where you can find an electron bead. So it's all mathematics, and it's all circular. It has nothing to do with physics. Can't tell you why an atom, like in this case, a carbon atom, binds or merges with hydrogen to form, methane. They can't tell you physically what's happening there. So they say, look, we can describe it mathematically, but they insist that the electron is a bead that's rolling around. And of course, with a little bead, they cannot explain attraction.
Can you pull up the rope model again real quick?
Yeah, the rope model, here it is. Here it is. Okay, and you can see it. We're going to replace that thing with, first we get rid of the axis. Okay, then because we don't need the mathematical nonsense. So all we need is to show that the atom is a balloon. It's made by all the ropes that are converging upon that atom, and you can describe any point along there with a radius, latitude.
I want to clarify that balloon isn't made out of rope; it's made out of the thread. So can you clarify that real quick? Yeah,
there's two threads. They're twined, that's the rope. One thread goes to the center of the atom. That's the ray that forms the proton, what I call dandelion. It's a little dandelion made out of the one thread of that rope. In other words, from every atom in the universe, okay? And one thread goes into, one of those threads forks out at the electron shell, continues to the center of the atom, and all those threads from every atom in the universe forms the proton dandelion. The other thread goes around, curves around, and forms the electron shell and forms the electron balloon, the encapsulating rubber, so to speak.
My question to that is there any physical mechanism that describes or explains why they would fork out like that?
It just is. No, it just is. It's like saying, this is what an atom looks like, okay? So what we're talking about, we're saying, what does an atom look like? And I
was trying to wonder, what dictates the distance from the center to the shell?
It changes from atom to atom, and depends on how big the atom is, how many shells are merged, because every atom gets more and more complicated, as you get to heavier and heavier elements.
The balloon one
you got balloons on top of balloons. Imagine one of these clowns that twists balloons and makes little different things with them. The atoms get very complicated as you get along, because all these balloons are merged together, to form bigger and bigger balloons, bigger structures made out of balloons, okay? But the point that I'm trying to make here is, let's understand first the simple one. That's complicated enough, but at the same time it's complicated. It's very simple. Just imagine a balloon, and all the ropes are connected to that balloon from every atom in the universe, just connected to one round spherical balloon, okay? At the electron shell, at the surface of the electron shell, they fork out. The two threads that form the rope that interconnects all these atoms, they fork out. One goes straight to the center, the other one goes around. And then, so you have all these rays going into the center, and that forms that little dandelion in the center, and that's encapsulated by the one that went around. And so what happens? You have a ball that's encapsulating a little dandelion, and that's the hydrogen atom. But just imagine the universe of just hydrogen atoms. Let's forget about the heavier atoms. What you see is, all these balls, all these spheres, all these clouds, as these people refer to them.
Let's not talk about clouds.
Well, they call it a cloud, like a cloud that's encapsulating the nucleus. That's what it is.
Because cloud doesn't apply to this, because cloud is discrete.
Yeah, the reason they use the word cloud is because it vibrates, and so it's like nebulous. It's like, I can't pinpoint a perfect surface. It's like vibrating. It's like, a cloud, going around. So that's fine. I have no problem with the word cloud. I have no problem with the word balloon. It's an encapsulating entity, like they showed in the orbitals here. It's an encapsulating entity. It's for real. Now we can talk about merging of shells, of why two atoms get together, because we're talking about a surface. We're talking about two balloons, which somehow, because of their properties, they can merge and form bigger, not only bigger atoms, but also molecules.
I had one last question about the one that forks out the thread that forks out to make the electron shell.
Yeah.
How many times does it go around the ball?
I would think only once. In other words,
a whole...
Yeah, but see, it could do a half a turn and come out the other end as another rope, and it could come out on the side, immediately on the side.
Wouldn't it be slack? if it's just.
I think it is slack because the thread curves around, so it's already slacking if it's curved and it's vibrating and it's twirling around itself.
Oh, there's a lot of movement.
There's a lot of motion. In fact, the fourth number here. Let's see if I can put that back up here. The fourth number. Look at the fourth number when it comes up here. Yeah, look at the fourth number as it comes up. You got radius, latitude, and longitude. Okay. And then there's a fourth number on the GIF here, in situ spin or rotation of the magnetic thread. So the thread is spinning in situ, okay? And that's important because that is the fourth number in, that you need to do Schrodinger's equation, in other words.
Can we go more into the rope model tomorrow?
Yeah. In fact, we will try to continue with it because there's a lot of subjects to be covered, and I'll give you. I shouldn't do this. I like to surprise people, but what I'm going to be ending the week with, hopefully, or maybe covering it tomorrow, quantum computing, quantum computers, how we get there, and that's a big phrase these days. You should be aware of. I want to caution you on what really is meant by quantum computing and how it's used as propaganda for quantum mechanics. But that's subject matter for one of the next 3 days, whenever we get to it. We got decoherence, we have tunneling, we have entanglement. There's a lot of subjects to cover still before we get there. And then when you put it all together, you say, oh, now I kind of understand what all this is about. And I just want you to get a ballpark idea of what's going on here and what these people do for a living. Okay, and what they do for a living is fool you. That's what they do for a living. We'll see you tomorrow, same time, same station. Bye-bye.